In this lecture, we answer two questions. In the first question, we find out the area of this rectangle ABCD, and in the second question, we find out the area of this trapezoid ABCD. So we start with the first question. In the drawing, we have a circle that is inscribed by rectangle ABCD. In addition, we know that this is called EF, that is equals to 12 units in its length. This is line segment FG, that is equals to 10 units in its length. Again, our mission is to find out the area of this rectangle ABCD. So first of all, we know that all the angles inside the rectangle are right angles. So this angle is a right angle. We will define the length of rectangle ABCD. AB, we define AB as the length of rectangle ABCD. And the width will be dA. We know that the area of an rectangle equals to the length of the rectangle times the width. We will also define the radius of this circle as R. And we'll join points O and N together by a straight line. Point O is the center of the circle, point N is the point on the circle itself. Therefore, ON is the radius of this circle that is equals to R according to our definition. The radius ON that is equals to R, the radius ON is drawn to point N, that is the point of tendency of tangent AB with this circle. And whenever you have a radius that is drawn to the point of tendency, again, the radius ON is drawn to point N, that is the point of tendency of tangent AB with this circle. Whenever you have a radius that is drawn to the point of tendency, then tangent AB will be perpendicular to the radius NO. If AB is perpendicular to NO, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to rule 1. Likewise, we join points O and M together by a straight line. OM is of course the radius of this circle that is equals to R. The radius OM is drawn to point M, that is the point of tendency of tangent DC with this circle. Whenever you have a radius that is drawn to the point of tendency, then tangent DC will be perpendicular to the radius MO. If this is perpendicular to MO, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to the same rule, rule 1. We join points O and D together by a straight line. OE is of course the radius of this circle that is equals to R. Again, the radius OE is drawn to point E, that is the point of tendency of tangent DA with this circle. Whenever you have a radius that is drawn to the point of tendency, then tangent DA will be perpendicular to the radius EO. If DA is perpendicular to EO, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to the same rule, rule 1. By doing this construction, we're going to do the small quadrilateral DMOE. Inside this small quadrilateral DMOE, we have 1, 2, 3 right angles. The sum of 3 right angles is 270 degrees. So 270 degrees plus the size of this fourth missing angle. In total, they must be equal to 360 degrees according to the rule that says that the sum of the angles in any quadrilateral is equal to 360 degrees. Therefore, this fourth missing angle must be equal to 90 degrees in its size. Likewise, in the lower quadrilateral EONA, we have 1, 2, 3 right angles. The sum of 3 right angles is 270 degrees, so 270 degrees plus the side of this fourth missing angle, in total it must be equal to 360 degrees according to the sum rule that says that the sum of the angles in any quadrilateral is equal to 360 degrees. And therefore this fourth missing angle must be equal to 90 degrees in its size. So the big angle MON is equal to 90 degrees plus 90 degrees, that is 180 degrees. So I write it down. Angle MON is equal to 180 degrees in its size. And we know that any angle that is equal to 180 degrees in its size is defined as a straight line. Therefore, line segment MON is a straight line. If line segment MON is a straight line, then MN is also a straight line. But MN is a straight line that touches the circle at 2 points, point M and point N. Therefore, MN is a chord. It is a chord that passes through point O, that is the center of the circle. And we know that any chord that passes through the center of the circle must be the diameter of the circle. Therefore, MN is the diameter of the circle. So MN is a chord that passes through the center of the circle. That is to say point O, and therefore MN is the diameter of the circle. So write it down. Here, MN is the diameter of the circle. In the next step, we will extend the radius EO by a straight line until it touches the circle. And we will define the touching point of the extended radius EO with this circle, and this point is point L. EO is a radius, and therefore it is absolutely a straight line. We extended the straight line EO by straight line, the result EL must be also a straight line, because when you extend a straight line by a straight line, the result must be a straight line. So EL is a straight line that touches the circle at 2 points, E and L, therefore EL is a chord. EL is a chord that passes from point O, that is the center of the circle, therefore EL, and you know that any chord that passes through the center of the circle must be the diameter of the circle. Therefore EL is the diameter of the circle. So write it down, EL is the diameter of the circle. EL is the diameter of the circle. And we have already found out that MN is the diameter of the circle. Anyway, MN is the diameter of the circle. It is absolutely a straight line. Therefore, the shape DMNA has 4 sides. 1, 2, 3, 4. Therefore, shape DMNA is a quadrilateral. Okay, shape DMNA is a quadrilateral with 4 right angles, and according to Rule 5, any quadrilateral that has 4 right angles must be less rectangle in front of square. So we relate to the big quadrilateral DMNA as rectangle because it has 4 right angles. So let me know. Quadrilateral DMNA is a rectangle according to Rule 5. But we also know that the opposite sides of a rectangle are equal to each other. So in the big rectangle DMNA, side DA must be equal to the opposite side MN. So now, in rectangle, the big rectangle DMNA, side DA must be equal to the opposite side MN. According to the rule that the opposite sides of a rectangle are equal to each other. DA is the width of rectangle ABCD, so you can write here that DA is the width of rectangle ABCD, and MN is the diameter of the circle. So you can write here that MN is the diameter of the circle. But we have already found out that EL is also the diameter of the circle. So you can write here that EL is the diameter of the circle also. EL is the diameter of the circle. And from this log equation, the width equals to DA equals to MN equals to the diameter equals to EL. We will derive that EL is the width of rectangle ABCD. EL is the width of a rectangle ABCD. Okay, EL is the width. In the next step, we will join points L and F together by straight line. By joining points L and F, we created peripheral angle LFE. Peripheral angle LFE subtends on EL, that is the diameter of the circle, And we know that any peripheral angle that subtends on the diameter of this circle must be equal to 90 degrees in its size according to rule 7. So please click on rule 7. According to rule 7, if a peripheral angle subtends on the diameter of the circle, then it is equal to 90 degrees in its size. So in the drawing you have a circle, and AB is the diameter of this circle. This is peripheral angle ACB that subtends on AB, that is the diameter of this circle, and therefore peripheral angle ACB is equal to 90 degrees in its size. So in our drawing, peripheral angle LFE subtends on EL, that is the diameter of this circle, therefore peripheral angle LFE must be equal to 90 degrees in its size according to rule 7. We will define angle LEF. This angle is alpha. So in the right angle ELF, this angle equals to alpha, this angle equals to 90 degrees. Therefore, this perpendicular angle must be equal to 90 degrees minus alpha. Why? Because 90 degrees minus alpha plus alpha is 90 degrees, and 90 degrees plus 90 degrees, it is equal to 180 degrees. That is the sum of the angles in any triangle. In the next step, we will extend the diameter EL by a straight line until it touches side CB of rectangle ABCD. Repeat again, we will extend the diameter EL of this circle by a straight line until it touches side CB of rectangle ABCD. And we will define the touching point of the extended diameter EL with side CB. This point is point T. The diameter EL, it is absolutely a straight line. When you extend a straight line by straight line, the result is a straight line. So ET must be also a straight line. So by doing this construction, we can do quadrilateral ETBA. Inside quadrilateral ETBA, we have 1, 2, 3 rectangles. The sum of 3 rectangles is 270 degrees, so 270 degrees plus the size of this 4 pieces again. In total, it must be equal to 360 degrees according to the rule that said the sum of the angles in any quadrilateral is equal to 360 degrees. And therefore, this 4 pieces again must be equal to 90 degrees in its size. So inside the big quadrilateral ETBA, we have 4 angles, and according to rule 5, any quadrilateral that has 4 angles must be a rectangle in front of square. So we will go to the big quadrilateral ETBA is a rectangle because it has 4 angles. So I write it down. The big quadrilateral ETBA is a rectangle according to rule 5. But we also know that the opposite sides of a rectangle are equal to each other. So in the big rectangle ETBA, side ET must be equal to the opposite side AB. So I write it down. In rectangle ETBA, side ET must be equal to the opposite side AB. ET must be equal to the opposite side AB, but AB is the length of rectangle ABCD. So I can write here that AB is the length of rectangle ABCD, and from this equation, ET equals to AB equals to the length of rectangle ABCD. We will derive that ET is also the length of rectangle ABCD. So ET is the length of rectangle ABCD. So in total, we have found out that EL is the width of rectangle ABCD and ET is the length of rectangle ABCD. In the next step, we will focus on the big right triangle ETG. The big right triangle ETG, this angle equals to alpha, this angle equals to 90 degrees, therefore this front missing angle must be equal to 90 degrees minus alpha. Why? Because 90 degrees minus alpha plus alpha is 90 degrees, and 90 degrees plus 90 degrees, it is equal to 180 degrees. That is the sum of the angles in any triangle. It is very easy to see, to prove that the big right triangle ETG that is similar to the small right triangle ELF. So why those two right triangles are similar to each other? First of all, those two angles are both equal to 90 degrees minus alpha, therefore they are equal to each other. In addition, those two angles are both equal to 90 degrees and therefore they are equal to each other. This is angle E, it is also defined as angle alpha. Angle E is a common angle that belongs to both triangles. Angle E belongs to the small right triangle ELF, and angle E also belongs to the big right triangle ETG. So we can find out that angle E equals to itself as a common angle that belongs to both triangles. So in total, we should find out that all the triangles of the big right triangle ETG are correspondingly equal to all the triangles of the small right triangle ELF, and therefore those two right triangles are similar to each other according to angle similarity rule. So I write it down. I should find out that the big right triangle ETG is similar. This is the sign of similar to the small right triangle ELF. According to angle similarity rule. As for the fact that those two right triangles are similar to each other, we will derive that the following relationship exists between their sides. We will derive that side ET of the big right triangle ETG over side EF of the small right triangle ELF is equal to side EG of the big right triangle ETG over side EL of the small right triangle ELF. So repeat again, from the fact that those two right triangles are similar to each other, we will derive that the following relationship exists between their sides. That side ET of the big right triangle ETG over side EF of the small right triangle ELF is equal to side EG of the big right triangle ETG over side EL of the small right triangle ELF. ET is the missing side, so leave it as it is. Over EF. EF is 12. And it is equal to EG. EG in total equals to 12 plus 10, that is 22. Over EL. EL is the missing side, so leave it as it is. So in total, we found out that ET over 12 equals to 22 over EL. So here we will cross multiply this equation and we get that ET times EL is equal to 22 times 12. So ET times EL is equal to 22 times 12 is 264. ET times EL equals to 264. But we have already found out that ET is the length of rectangle ABCD and EL is the width. So we substitute ET by the length of rectangle ABCD and we substitute EL by the width of rectangle ABCD. And it is equal to 264. So in total, if we found out that the length of rectangle ABCD times the width of rectangle ABCD is equal to 264 square units, the length times the width is the area of rectangle ABCD. So the area of rectangle ABCD is equal to 264 square units. And that is the answer to the first question. Repeat again, if we found out that the area of this rectangle ABCD is equal to 264 square units. So we finished with the first question. In the next step, I present you the second question and we'll solve the second question of this lecture. In the second question, our task is to find out the area of this trapezoid ABCD. It is given us the question that AB equals to AP, PD equals to DC, BQ equals to 4 units in its length, QC equals to 9 units in its length. This is angle PQC, that is a right angle. Those two angles are also right angles. Again, our task is to find out the area of this trapezoid ABCD. So, we know that AB equals to AP. So, if we define the length of AB as A, that is to say AB equals to A units in its length, then the length of line segment AP must be also equal to A units in its length because they are equal to each other according to what is given us the question. Likewise, PD equals to DC, so if we define the length of PD as B, then the length of DC must be also equal to B because they are equal to each other according to what is given us the question. In the next step, we will join points B and P together by side 9. And we join points P and C together by step 9. By joining points B and P, we created the right triangle APB. This right triangle is also an associated triangle because AP equals to AB. And you have the rule that says that in front of equal sides in the triangle, there are equal angles. So in front of those two equal sides, we have those two angles that must be equal to each other in their sizes because of the fact that they are located in front of those two equal sides. So if we define the size of this angle as alpha, then the size of this angle must be also equal to alpha because they must be equal to each other according to the rule that I mentioned. We also know that the sum of the angles in any triangle is equal to 180 degrees. And that is so also in this right triangle, triangle PAB. So which angles we have in this right triangle PAB? This angle equals to 90 degrees, plus alpha, that is plus 2 alpha. In total, they must be equal to 180 degrees, according to the rule that the sum of the angles in any triangle is equal to 180 degrees. So here we subtract 90 degrees from the equation, and we get that 2 alpha equals to 180 degrees minus 90 degrees is 90 degrees. Here we divide this equation by 2, and finally we get that alpha equals to 90 degrees over 2, that is 45 degrees. So this is angle alpha, that is equal to 45 degrees in its size. And this is also angle alpha, that is equal to 45 degrees in its size. From this triangle, that is a right triangle and also associated triangle simultaneously, we derive that any right triangle that is also an associated triangle will always have the same three angles. One angle is a right angle, and the other two angles are those two angles that are 45 degrees each of them. So therefore, in this right and associated triangle, triangle PDC, it is a right angle. It is a right triangle. Triangle PDC is a right angle because this angle is a right angle, and it is an associated triangle because PD equals to DC. So in this right and associated triangle, in this right angle and associated triangle, triangle PDC, those two angles must be equal to 45 degrees each of them. This is true in any right and associated triangle. Always we will have one right angle, and the other two angles must be equal to 45 degrees each of them. You don't have to repeat on the same proof in order to determine that those two angles are equal to 45 degrees each of them. So we know that AD is one side of trapezoid ABCD, therefore it is absolutely a straight line. So if you focus on the right side of the straight line AD at point P here, the sum of the angles must be equal to 180 degrees according to rule 3 that states that the sum of the angles on one side of a straight line is equal to 180 degrees. So which angles we have at the right side of AD at point P? We have this angle that is 45 degrees, this angle is 45 degrees, in total there are 90 degrees. So 90 degrees plus the size of this missing angle, in total they must be equal to 180 degrees according to rule 3. Therefore this third missing angle must be equal to 90 degrees in its size. Why? Because 90 degrees plus 45 degrees plus 45 degrees in total is 180 degrees. That is the sum of the angles on the right side of AD at point P according to rule 3. So if we define the size of this angle as alpha, that is to say angle BPQ equals to alpha, then this missing angle must be equal to 90 degrees minus alpha. That is to say angle QPC must be equal to 90 degrees minus alpha. Why? Because 90 degrees minus alpha plus alpha is 90 degrees. That is the size of the big angle, angle BPC. Therefore this missing angle must be equal to 90 degrees minus alpha. So in the right big triangle PQC, this angle equals to 90 degrees minus alpha, this angle equals to 90 degrees. Therefore this third missing angle must be equal to alpha. Why? Because alpha plus 90 degrees minus alpha is 90 degrees, and 90 degrees plus 90 degrees, it is equal to 180 degrees. That is the sum of the angles in any triangle. BC is one side of trapezoid ABCD, therefore it is absolutely a straight line. So if we focus on the left side of the straight line BC at point Q, here the sum of the angles must be equal to 180 degrees according to rule 3 that says that the sum of the angles from one side of a straight line is equal to 180 degrees. So which angles we have at the left side of the straight line BC at point Q? We have this angle that is equal to 90 degrees. So this angle plus this missing angle in total they must be equal to 180 degrees according to rule 3. Therefore this missing angle must be equal to 90 degrees in its size. So in the right small triangle PBQ, this angle equals to alpha, this angle equals to 90 degrees. Therefore this third missing angle must be equal to 90 degrees minus alpha. Why? Because 90 degrees minus alpha plus alpha is 90 degrees, and 90 degrees plus 90 degrees, it is equal to 180 degrees. That is the sum of the angles in any triangle. In the next step, we will prove that the small right green triangle PBQ is similar to the big right triangle PQC. So why those two right triangles are similar to each other? First of all, those two angles are both equal to 90 degrees minus alpha, therefore they are equal to each other. In addition, those two angles are both equal to alpha, therefore they are equal to each other. And finally, those two angles are both equal to 90 degrees, and therefore they are equal to each other. So I shall prove that all the angles of the right big triangle PQC are correspondingly equal to all the angles of the green small right triangle PBQ. And therefore, those two right triangles are similar to each other according to angle similarity rule. So I write it down. We actually found out that the big right triangle PQC is similar. This is the sign of similar to the small green right triangle PBQ according to angle similarity rule. And from the fact that those two right triangles are similar to each other, we will derive that the following relationship exists between their sides. But before that, side PQ is a common side that belongs to both triangles. Side PQ belongs to the green triangle PQB, and side PQ also belongs to the big right triangle PQC. So from the fact that those two right triangles are similar to each other, we will derive that the following relationship exists between their sides. We derive that side PQ of the big right triangle PQC over side BQ of the small green triangle PBQ is equal to side QC of the big right triangle PQC over side PQ of the small right triangle PBQ. So repeat again, we found out that PQ over BQ equals to QC over PQ. PQ is the missing side, so we leave it as it is. Over BQ, BQ is 4, according to what is given as the question, and it is equals to QC. QC is 9 over PQ. So in total, we found out that PQ over 4 equals to 9 over PQ. Here we will cross multiply this equation. And we get that PQ times PQ is PQ square. And PQ square equals to 9 times 4, that is 36. So here we take a root out of this equation and finally get that PQ equals to the square root of 46, that is 6. So we found out that the missing side PQ is equal to 6 units in its length. In the next step, we will implement the Pythagoras theorem on the big right triangle PBC. According to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. Here by PT is a version from Pythagoras theorem. So in the right big triangle BPC, BC is the hypotenuse, therefore the square of the hypotenuse is BC square, and BC square must be equal to BP square plus PC square. Okay, again, according to the Pythagoras theorem in the big right triangle BPC, BC square, that is the square of the hypotenuse, equals to BP square plus PC square. BC in total equals to 4 plus 9, that is 13, therefore BC square is 13 square, that is 169. And it is equal to BP square. What is the value of BP square? In order to find out the value of BP square, we will implement the Pythagoras theorem on the right small triangle APB. On the right small triangle APB, according to the Pythagoras theorem, A square plus A square equals to BP square. So BP square in total equals to A square plus A square, that is 2A square. BP square equals to 2A square plus PC square. What is the value of PC square? In order to find out the value of PC square, we will implement the Pythagoras theorem on the right triangle PDC. According to the Pythagoras theorem on the right triangle PDC, B square plus B square equals to PC square. So PC square in total equals to B square plus B square, that is 2B square. So PC square is 2B square. So in total, we should find out that 169 equals to 2A square plus 2B square. So 169 is equal to 2 times A square plus B square. Here we took 2 as a common factor from those two expressions, so inside the brackets we have A square plus B square. So in total, we actually found out that 169 equals to 2 times A square plus B square. Here we divide this equation by 2, and finally we get that A square plus B square equals to 169 over 2. Please again, found out that A square plus B square equals to 169 over 2. Our mission is to find out the area of this trapezoid ABCD. So what is the area of trapezoid ABCD? Actually, the area of trapezoid ABCD is equal to the sum of the areas of the three components that trapezoid ABCD consists of. Trapezoid ABCD consists of three components. It consists of the small right triangle ABP, and it is also consists of the big right triangle PBC, and the first component is the right triangle PDC. So the sum of the areas of those three components in total they must be equal to the area of trapezoid ABCD. So the first component is triangle, the right triangle ABP. So and therefore the area of the first component is the area of triangle ABP. The area of the first component is the area of the right triangle ABP plus the area of the second component, that is the area of triangle, the big triangle PBC, the big right triangle PBC. Plus the area of the third component, that is the area of this triangle PDC, the right triangle PDC. So repeat again, we actually found out that the area of trapezoid ABC, the area of trapezoid ABCD is equal to the sum of the areas of the three components that triangle that the trapezoid ABCD consists of. The area of the first component is the area of the right triangle ABP. The second component is the big triangle PBC, therefore plus the area of the second component, that is the area of the big right triangle PBC, plus the area of the third component, that is the area of the right triangle PDC. So we find out the area of each component separately, and then we will add the three areas together, and the result will give us the area of trapezoid ABCD. So what is the area of the first component? That is the area of this right small triangle ABP. The area of any triangle equals to the base of the triangle times the height over 2. The base of this right triangle ABP is AB, the height is AP over 2. AB is A, AP is A. So AB times AP is A times A, that is A squared over 2. So in total, if we found out the area of this triangle ABP is equal to A squared over 2. Plus the area of the second component that trapezoid ABCD consists of, that's actually the area of this big right triangle PBC. What is the area of the big right triangle PBC? It is equal to the base BC times the height QP over 2. Why the height is QP? Because of the fact that QP creates 90 degrees with the base BC. Those two angles are right angles. So in total, the area of the big right triangle PBC it is equal to the base BC times the height QP over 2 plus the area of the first component, that is actually the area of this right triangle PDC. What is the area of the right triangle PBC? It is equal to the base DC times the height DP over 2. DC is B, DP is also P, so it is B times B, that is B squared over 2. So in total, the area of this right triangle PDC is equal to B squared over 2. So the area of trapezoid ABCD in total will be equal to A squared over 2 plus B squared over 2 is A squared plus B squared over 2 plus the area of the big right triangle PBC. The big right triangle PBC equals to BC. BC in total equals to 4 plus 9, that is 13, times QP. QP is 6 divided by 2. So in total, if we found out that the area of the big right triangle PBC is equal to 13 times 6 over 2. Here, A squared plus B squared over 2. We have already found out that A squared plus B squared equals to 169 over 2. Therefore, we substitute we will substitute a squared plus b squared in this expression by 169 over 2, and we have to divide it by 2. So in total, this expression will be equal to 169 over 2 times 2, plus 13 times 6 over 2. 13 times 6 over 2 is 6 over 2 is 3, and 3 times 14 is 39. So in total, this expression equals to 39. So the area of trapezoid ABCD is equals to 169 times 2 times 2. 2 times 2 is 4, so it is 169 over 4 plus 39. So here we multiply 39 by 4, and then we divide it by 4 in order to have a common factor with this number. And we get that in total the numerator will have 169 plus 39 times 4 is 156 divided by 4. 169 plus 156 is 325 over 4. 325 over 4 is 81.25 square units. So actually, the answer to the second question is that the area of this trapezoid, trapezoid ABCD is equal to either 325 over 4 square units, or in terms of numbers, the area of this trapezoid ABCD is equal to 81.25 square units. So we finish with the second question. In the next step, I'm summarize the lecture. I'll start with the first question, of course. Our test in the first question is to find out the area of this rectangle ABCD. So in the drawing we have rectangle ABCD, and this circle is inscribed by rectangle ABCD, or rectangle ABCD blocks this circle. In addition, you know that this is called EF, that is equal to 12 units in its length. This is line segment FG, that is equal to 10 units in its length. Again, our task is to find out the area of this rectangle ABCD. So first of all, we know that all the angles inside the rectangle are right angles. So this means again equals to 90 degrees in size. We defined the length of the rectangle ABCD as AB, and the width as AD. You know that the area of any rectangle equals to the length of the rectangle times the width. We define the radius of this circle as R. We join points O and N together by a straight line. Point O is the center of the circle, point N is the point of the circle itself, therefore ON is the radius of this circle that is equals to R according to our definition. The radius ON that is equals to R, the radius ON is 1 to point N, that is the point of tendency of tangent AB with this circle. Whenever your radius is 1 to the point of tendency, then tangent AB will be perpendicular to the radius NO. So if AB is perpendicular to NO, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to rule 1. Likewise, we join points O and N together. We join points O and M together by a straight line. OM is the radius of the circle that is equal to R. The radius OM is 1 to point M, that is the point of tendency of tangent DC with this circle. Whenever you have a radius that is 1 to the point of tendency, then tangent DC will be perpendicular to the radius MO. If this is perpendicular to MO, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to the same rule, rule 1. In the next step, you join points O and E together by a straight line. OE is the radius of this circle that is equals to R. The radius OE is 1 to point E, that is the point of tendency of tangent AD with this circle. And whenever your radius is 1 to the point of tendency, then tangent AD will be perpendicular to the radius EO. if AD is perpendicular to EO, it means that this angle was 90 degrees and this angle also equal to 90 degrees according to the same rule 1. By doing this construction, we added the small quadrangle DMOE. Inside the small quadrangle DMOE, we have 1, 2, 3 right angles. The sum of 3 right angles is 270 degrees. So 270 degrees plus the size of this 415 again, in total must be equal to 360 degrees according to the rule that said that the sum of the angles in any quadrangle is equal to 360 degrees. And therefore this 415 again must be equal to 90 degrees in its size. Likewise in the lower quadrangle EONA, we have 1, 2, 3 right angles. The sum of 3 right angles is 270 degrees, so 270 degrees plus the size of this 4 pieces again, in total must be equal to 360 degrees according to the rule that says that the sum of the angles in any quadrangle is equal to 360 degrees. Therefore this 4 pieces again must be equal to 90 degrees in its size. So in total, if we found out that the big angle MON is equal to 90 degrees plus 90 degrees, that is 180 degrees. So MON equals to 180 degrees in its size, and we know that any angle that is equal to 180 degrees in its size, it is defined as a straight line. So line segment MON is a straight line. Line segment MON is a straight line. If line segment MON is a straight line, then MN is also a straight line. MN is a straight line that touches the circle at 2 points M and N, and therefore MN is a chord. MN is a chord that passes for point O, that is the center of the circle, and we know that any chord that passes for the center of the circle must be the diameter of the circle. Therefore, MN is the diameter of the circle. And again, MN is the diameter of the circle. In the next step, we actually found out that MN is the diameter of the circle, so MN is the diameter, it is absolutely a straight line, so this shape DMNA consists of 4 sides, and therefore it is a quadrilateral. So DMNA is a quadrilateral that has 4 right angles, and according to rule 5, any quadrilateral that has 4 right angles must be at least a right angle if not a square. So, related to the big quadrilateral DMNA is a rectangle. Why? Because it has 4 right angles. But we also know that the opposite sides of a rectangle are equal to each other. So, in the big rectangle DMNA, side MN must be equal to the opposite side DA. It again, in the big rectangle DMNA, side DA must be equal to the opposite side MN. But DA is the width according to our definition. DA is the width. And we just like to find out that MN is the diameter. Okay. So in the next step, we extended the radius EO of the circle by a straight line until it touches the circle at this point. We define the touching point of the extended radius EO of this circle. This point is point L. So EO is a radius, it is absolutely a straight line. When you extend a straight line by straight line, the result must be also a straight line. So EL must be a straight line. EL is a straight line that touches the circle at 2 points E and L, and therefore EL is a chord. EL is a chord that passes for point O, and we know that any chord that passes for the center of the circle must be the diameter of the circle. Therefore, if we found out that EL is the diameter of the circle. Again, EL is the diameter of the circle. So we can add to this long equation that EL is the diameter. And from this long equation, the width equals to DA equals to MN equals to the diameter equals to EL. We will derive that EL is the width of rectangle ABCD. Okay? EL is the width of rectangle ABCD. In the next step, we join points F and L together by a straight line. By joining points F and L, we can then peripheral angle LFE. Peripheral angle LFE subtends on EL, that is the diameter of the circle, and therefore according to rule 7, any peripheral angle that subtends on the diameter of the circle must be equal to 90 degrees in its size. Therefore, triangle NFE is right angle according to all 7. So, in the right triangle EFL, we define this angle as alpha. So, this angle is alpha, this angle is 90 degrees, and therefore this first angle must be equal to 90 degrees minus alpha. Why? Because 90 degrees minus alpha plus alpha is 90 degrees, and 90 degrees plus 90 degrees, it is equal to 180 degrees. That is the sum of the angles in any triangle. In the next step, we extended the diameter EL by straight line until it touches side CB of rectangle ABCD. Again, we extended the diameter EL by straight line until it touches side CB of rectangle ABCD. And we define the touching point of the extended diameter EL with this side CB. This point is point T. When you extend the straight line by straight line, the result is a straight line. So EL as the diameter is a straight line. We extended the straight line EL by straight line. The result is ET. So ET must be also a straight line. By doing this construction, we get the big quadrangle ETG. We get the big quadrangle ETBA. Inside the big quadrangle ETBA, we have 1, 2, 3 rectangles. The sum of 3 rectangles is 270 degrees, so 270 degrees plus the size of these 4 pieces again. In total, they must be equal to 360 degrees according to the rule that said that the sum of the angles in any quadrangle is equal to 360 degrees. And therefore, these 4 pieces again must be equal to 90 degrees in its size. So inside quadrangle ETBA, we have 4 rectangles. And according to rule 5, any quadrangle that has 4 rectangles must be this rectangle if not a square. So we went to the big quadrangle ETBA is a rectangle because it has 4 rectangles. But we also know that the opposite sides of a rectangle are equal to each other. So in the big rectangle ETBA, side ET must be equal to the opposite side AB. And again, in the big rectangle ETBA, side ET must be equal to side BA. In rectangle ETBA, side ET must be equal to side AB. But AB is the length. AB is the length according to our definition. AB is the length. And from this equation, ET equals to AB equals to the length. We will derive that ET is also the length of rectangle ABCD. So in total, we should find out that EL is the width of rectangle ABCD and ET is the length of rectangle ABCD. Again, so here we focus on the big triangle ETG. The big triangle ETG, this angle equals to alpha, this angle equals to 90 degrees. Therefore, this first angle must be equal to 90 degrees minus alpha. Why? Because 90 degrees minus alpha plus alpha is 90 degrees, and 90 degrees plus 90 degrees is equal to 180 degrees. That is the sum of the angles in a triangle. In the next step, we prove that the big right triangle ETG is similar to the small right triangle ELF. So why those two right triangles are similar to each other? First of all, those two angles are both equal to 90 degrees minus alpha, therefore they are equal to each other. In addition, those two angles are both equal to 90 degrees and therefore they are equal to each other. And finally, this is angle E, that is a common angle that belongs to both triangles. So we can write down that angle E equals to itself is a common angle that belongs to both triangles. So we should prove that all the figures of the big right triangle ETG are correspondingly equal to all the figures of the small right triangle ELF. And therefore those two right triangles are similar to each other according to angle similar to. And again, we should find out that the big right triangle ETG is similar, this is the sign of similar, to the right small triangle ELF according to angle similar to. And from the fact that those two right triangles are similar to each other, we will derive that the following relationship exists between their sides. We will derive that side ET of the big right triangle ETG over side EF of the small right triangle ELF is equal to side EG of the big right triangle ETG over side EL of the small right triangle ELF. So I'll repeat again. From the fact that those two right triangles are similar to each other, we know that side ET of the big right triangle ETG over side EF of the small right triangle ELF is equal to side EG of the big right triangle ETG over side EL of the small right triangle ELG. ET is the missing side, so we leave it as it is. EF is 12, EG is 22 because it is 12 plus 10, that is 22. EL is the missing sign, so we use the city. So in total, we should found out that ET over 12 equals to 22 over EL. Here we cross multiply this equation and finally found out that ET times EL equals to 22 times 12. So ET times 12 equals to 22 times 12 is 264. We already found out that ET is the length of rectangle ABCD and EL is the width. So we substitute ET by the length and EL by the width. And in total, we found out that the length of rectangle ABCD times the width is equal to 264. The length times the width is the area of rectangle ABCD. So in total, we found out that the area of this rectangle ABCD is equal to 264 square units. So we finish with the first question. In the next step, I presented to you the second question, and you solve the second question of this lecture. In the second question, our task is to find out the area of this trapezoid ABCD. It is given us the question that AB equals to AP, PD equals to DC, BQ equals to 4 units in its length, QC equals to 9 units in its length. This is angle PQC, that is right angle. Those two angles are also right angles. Again, our task is to find out the area of this trapezoid ABCD. So first of all, we know that AB equals to AP. If only to what is given as a question, so if we define the length of AB as A, then the length of AB must be also equal to A because they are equal to each other. Likewise, we know that PD equals to DC. So if we define the length of PD as B, then DC must be also equal to B because they are equal to each other. Okay. In the next step, we join points B and P together by straight line, and we join points B and C together by straight line. By joining points B and P, we created the right fourth triangle, ABP. This is also an isosceles triangle. And we know that AB equals to AP, and in front of those two equal sides in the triangle, there are those two angles that must be also equal to each other and their sides. So if we define this angle as alpha, then this angle must be also equal to alpha because they are equal to each other according to the rule that we mentioned. So in the right triangle ABP, the sum of the angles must be equal to 180 degrees. So which angles we have in the right triangle ABP? We have this angle that is the right angle, plus alpha that is plus 2 alpha, and total it must be equal to 180 degrees. So here we subtract 90 degrees from this equation. If I found out that 2 alpha equals to 180 degrees minus 90 degrees is 90 degrees. Here we divided this equation by 2. We finally found out that alpha equals to 90 degrees over 2, that is 45 degrees. Okay. So this is angle alpha. This is angle alpha that is equal to 45 degrees. In its side, this is also angle alpha that is equal to 45 degrees. So from this specific triangle that is a right and isosceles triangle at the same time, we will derive that in any right and isosceles triangle, we have one angle that is right angle, and the two other angles must be equal to 45 degrees, each of them. Therefore, this is the right triangle PDC. This is also an isosceles triangle because PD equals to DD, PD equals to DC. We have one right angle, and those two angles must be equal to 45 degrees, each of them. In order to prove that those two angles are equal to 45 degrees, because we have already done it here. Okay, so AD is one side of trapezoid ABCD, therefore it is absolutely a straight line. So if we focus on the right side of the straight line AD at point P, here the sum of the angles must be equal to 180 degrees according to rule 3 that said that the sum of the angles on one side of a straight line is equal to 180 degrees. So which angles we have at the right side of AD at point P? We have this angle that is 45 degrees, plus this angle that is 45 degrees, in total it is 90 degrees, plus this third missing angle, in total they must be equal to 180 degrees according to all three. So this missing angle must be equal to 90 degrees and its size. Y equals 90 degrees plus 45 degrees plus 45 degrees, it is equal to 180 degrees. It is the sum of the angles on the right side of AD, it's 0.3 according to all three. Therefore this third missing angle must be equal to 90 degrees and its size. So if we define the small angle BPQ as alpha, then the big angle QPC must be equal to 90 degrees minus alpha. Y equals 90 degrees minus alpha plus alpha is 90 degrees, that is the size of the big angle BPC. Therefore this missing angle must be equal to 90 degrees minus alpha. So in the right triangle PQC, this angle equals to 90 degrees, this angle equals to 90 degrees minus alpha, therefore this third missing angle must be equal to alpha. Y equals alpha plus 90 degrees minus alpha is 90 degrees, and 90 degrees plus 90 degrees, it is equal to 180 degrees. That is the sum of the angles in a triangle. Okay. Likewise, but before that we know that BC is one side of trapezoid ABCD, therefore it is absolutely a straight line. So if we focus on the left side of the straight line BC at point Q, here the sum of the angles must be equal to 180 degrees according to all three. So which angles we have at the left side of BC at point Q? We have this angle that is right angle, plus this missing angle, in total the sum of those two angles must be equal to 180 degrees according to all three. Therefore this missing angle must be equal to 90 degrees in size. So in the small right triangle BPQ, this angle equals to alpha, this angle equals to 90 degrees, therefore this missing angle must be equal to 90 degrees minus alpha. Y equals 90 degrees minus alpha plus alpha is 90 degrees. 90 degrees plus 90 degrees, it is equal to 180 degrees, that is the sum of the angles in a triangle. In the next step, we prove that the green triangle BQP is similar to the big right triangle PQC. So why those two right triangles are similar to each other? First of all, those two angles are both equal to alpha, therefore they are equal to each other. In addition, those two angles are both equal to 90 degrees minus alpha, therefore they are equal to each other. And finally, those two angles are both equal to 90 degrees, and therefore they are equal to each other. So if you prove that all the angles of the big right triangle PQC are correspondingly equal to all the angles of the green small right triangle BPQ. Therefore, those two right triangles are similar to each other according to angle similarity rule. Again, we should prove that the triangle PQC is similar to the small right triangle BPQ according to angle similarity rule. And from the fact that the green triangle BPQ is similar to the big triangle PQC, we derive that the following relationship exists between their sides. PQ is a common side that belongs to both triangles. PQ belongs to the green triangle, and PQ also belongs to the big right triangle PQC. So from the fact that those two right triangles are similar to each other, we will derive that the following relationship exists between their sides. We will derive that side PQ of the big right triangle PQC over side BQ of the small right triangle BQP is equal to side QC of the big right triangle PQC over side PQ of the small right triangle PBQ. And again, we derive that PQ over BQ equals to QC over PQ. PQ is the missing side, so we will say that BQ is 4, QC is 9. Divided by PQ, that is the missing side. So in total, we actually found out that PQ over 4 equals to 9 over PQ. Here we first multiply this equation and finally found out that PQ times PQ is PQ squared, and it is equals to 9 times 4, that is 36. So PQ squared equals to 36. We took out of this equation and finally found out that PQ equals to the square root of 36, that is 6. So this is the missing side PQ that is equals to 6 units in its length. In the next step, we implemented the Pythagoras theorem on the big right triangle PBC. According to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. The hypotenuse in the big right triangle PBC is BC, therefore the square of the hypotenuse is BC squared, and BC squared must be equal to BP squared plus PC squared. Again, in the right triangle PBC, ABC according to the Pythagoras theorem. BC squared, that is the square of the hypotenuse, equals to BP squared plus BC squared. BC in total is 4 plus 9, that is 13, therefore BC squared is 14 squared, that is 169, and it is equals to BP squared. What is the value of BP squared? In order to find out the value of BP squared, we implement the Pythagoras theorem on the small right triangle APB. According to the Pythagoras theorem on the small right triangle APB, A squared plus A squared equals to PB squared. So PB squared equals to A squared plus A squared, that is 2A squared. Okay, again, BP squared equals to 2A squared plus PC squared. PC, what is the value of PC squared? In order to find out the value of PC squared, we implement the Pythagoras theorem on this right triangle PDC. According to the Pythagoras theorem on this right triangle PDC, B squared plus B squared equals to PC squared. So PC squared equals in total to 2B squared. So again, PC squared equals to 2B squared. So in total, we actually found out that 169 equals to 2A squared plus 2B squared. So 169 equals to, here we took 2 as a common factor from those two expressions, so inside the brackets we left only with A squared plus B squared. So 169 equals to 2 times A squared plus B squared. Here we divided the equation by 2 and finally found out that A squared plus B squared equals to 169 over 2. Our mission is to find out the area of this trapezoid ABCD. So what is the area of trapezoid ABCD? The area of trapezoid ABCD must be equal to the sum of the areas of the three components the trapezoid ABCD consists of. The first component is the right small triangle ABP, the second component is the right big triangle PBC, and the third component is this right triangle PDC. So the sum of the areas of those three components must be equal to the area of trapezoid ABCD. So again, if we found out that the area of trapezoid ABCD must be equal to the sum of the three components, the sum of the areas of the three components that trapezoid ABCD consists of. The first component is triangle ABP, therefore it is the area of the right triangle ABP plus the area of the second component, that is the area of triangle PBC, plus the area of the third component, that is the area of the right triangle PDC. So we find out the area of each component separately, and then we add the areas together, and the result will be the area of trapezoid ABCD. The first component is the area of triangle ABC, triangle ABP. We know that the area of any triangle is equal to the base of the triangle times the height over 2. Therefore, the area of this small right triangle ABP will be equal to AB times AP over 2. AB is A, AP is also A, so it is A times A over 2. There's actually A squared over 2. So if you found out that the area of the first component, that is the area of triangle ABP, is equal to A squared over 2. Plus the area of the second component. The second component is the big right triangle PBC. The area of the big right triangle PBC will be equal to the base BC times the height QP over 2. So again, the area of the big right triangle PBC is equal to the base BC times the height QP over 2. Plus the area of the first component, that is the area of the right triangle PDC. What is the area of the right triangle PDC? Is equal to the base DC times the height, that is dP over 2. So it is B times B over 2, that is actually B squared over 2. So the area of the first component is the area of the right triangle PDC, that is actually B squared over 2. A squared over 2 plus B squared over 2 is A squared plus B squared over 2, plus the area of the big right triangle PBC. And it is equal to BC. BC in total is 4 plus 9, that's 13. PQ is 6. But again, BC is 13. PQ is 6 divided by 2. So in total, the area of trapezoid ABCD is equal to A squared plus B squared over 2 plus 13 times 6 over 2. First of all, 13 times 6 over 2 is 6 over 2, that is 3 times 13, that is 39. So this expression in total equals to 39. And we have a squared plus b squared over 2. We already found out that a squared plus b squared equals to 169 over 2. Therefore, we can substitute a squared plus b squared here by 169 over 2 divided by 2. So in total, this expression equals to 169 over 2 times 2 plus 39. 2 times 2 is 4, so in total this expression equals to 169 over 4 plus 39. Here we multiplied 39 by 4 and then we divided by 4 in order to account factor with this number. And finally found out that in total in the numerator we have 169 and 4 times 39 is 156 divided by 4. And 169 plus 156 is 325 divided by 4. 325 over 4 is 81.25 square units. So in total, if you found out that the area of this trapezoid ABCD, that is the area that we're looking for in this question, it is equal to either 325 over 4 square units, so in terms of numbers, the area of this trapezoid ABCD is equal to 81.25 square units. Okay, thank you very much.